Hello, everyone. Welcome back. I hope you had a great little weekend there and a little break, early break. It was beautiful, wasn't it? Man, we had like summer weather. I hope you got out and were able to get away from your screens and enjoy the sunshine. I was able to go to the beach with my family, and it was just spectacular. Nice to have a little bit of summer in the middle of winter. So we're back at it here. Welcome. Thank you for all of you for turning on your cameras, and thank you, of course, for being here and coming to the live Zoom lecture. As you all know, these lectures are also posted on the Canvas site, so you can always rewatch them if you want, but I sure appreciate you all being here and turning on your cameras and allowing me to see your reactions, and it just makes it great for me. So let's see, before we get started, I don't really have any announcements yet. We haven't done very much, but we're gonna start chapter 14 today. Before I get started, do you have any questions? If you do, use the raise hand function in Zoom, and I'll call on you. Okay, I don't see any questions, so I'll go ahead and get started. Remember, if as we're going along, you have a question, just use the raise hand function on Zoom and I'll call on you. It may take me a moment or so to just finish whatever I'm talking about, but I will call on you and allow you to ask questions. And also remember that I'll always stick around after class is over for at least as much time as you need, at least an hour and 10 minutes or so. And I'm happy to answer questions then. And remember also, I have office hours on Tuesday and Thursday. If you would like to meet with me on any of those days, from 2 to 4, just send me an email. We can set up an appointment, okay? So I'm available. I want to help you. I want to see you all succeed. I see you doing your work on mastering chemistry and doing it well. So keep up with that. That's a big part of the learning process here. And it allows you to apply, it allows you to learn a little bit every day, right? And what I'm trying to get there is for you to constantly have a little chemistry on your brain, right? And so it gets lodged in there. Okay, I see one quick question from Elliot here. Elliot.
Hey, Professor. My question is Jello considered a solid or liquid?
Oh, interesting question. I think it'd be considered a solid, but it's kind of a funny state of matter, right? But I think it would be considered a solid. Yeah.
Okay. Thank you.
Okay, so the last chapter that we covered, right, was we sort of looked at liquids and solids, and we looked at some of their properties. Now we're going to jump into looking at solutions. And I want to start just with a little example of this little frog here, which is called a wood frog. And this frog is one of the few animals that can freeze in the winter and then thaw out and survive that process. Okay, so come when the weather gets cold, below freezing, this frog enters kind of a hibernatic kind of state and then actually freezes, and it becomes kind of like a frogsicle. And then it can stay frozen for months at a time throughout the winter, and then when the spring comes, it can thaw out, and when it thaws out, it hops off and starts looking for food because it's hungry because it hasn't eaten in a while. Now, super interesting, most things can't survive freezing. We talked about this a little bit last time. The reason they can't survive freezing is because when a cell freezes, the water inside of it expands. And when it expands, it can damage the cell, right? It could break cell walls, break membranes, things like that. So most living organisms do not survive freezing, but this frog does. How does it do it? It does it because it floods its cells with antifreeze, okay? So the cells get flooded with what we might call antifreeze. Actually, in this case, the antifreeze is just a solution of glucose and water. So let's start by defining a solution, okay? And a solution has a pretty broad definition. A solution is any homogeneous mixture. And do you remember from last semester the difference between a homogeneous mixture and a heterogeneous mixture? A heterogeneous mixture is something like salad dressing or oil and water, right? Where you mix them together, but they don't really mix at the molecular level, okay? And so they separate into different parts. Excuse me. A homogeneous mixture is the same throughout. So if you took a sample of a homogeneous mixture from any different part of it, you'd get the same consistency, the same mixture of components, okay? So a solution is any homogeneous mixture of two or more components. This particular mixture contains glucose and water, okay? Water is the solvent in this case, and the solvent is the majority component. And the glucose, which is this molecule right here, is, is the solute, which is the minority component. Okay. In this case, this is an example of an aqueous solution. And an aqueous solution is just a solution where water is the solvent. And most of our focus in this chapter is going to be on aqueous solutions. So anyway, what this frog does is before, when winter comes around, it floods its cells with this glucose solution, very, very concentrated glucose solution. And what we're going to learn in this chapter is that solutions have properties that are different from the properties of the pure solvent, okay? So water freezes at 0 degrees Celsius, but a concentrated glucose solution does not freeze at 0 degrees Celsius. So what does this do? This allows the liquid in the cell to remain a liquid instead of freezing solid, all right? The liquid that's outside of the cell of the frog, for example, the liquids in its stomach and other extracellular fluids, can freeze solid, and those don't burst the cell walls. However, within the cells remains liquid, and so you don't get any damage to the cells from freezing, right? So that's how this little frog can survive the frozen state. Taylor, you have a question?
Yeah, I'm assuming you can have multiple solutes, but can you have multiple solvents?
You can. So these definitions, eventually break down, because sometimes you can have, for example, you can have, multiple components in a solution and none of them are more than 50%. And so they break down. Or you can have a solution that's 50-50, let's say. So these are just guidelines that apply to most solutions. And so once you start having multiple components and you start having a lot of them, then the idea of solute and solvent just kind of fade to the background and you just have multiple components. Does that make sense?
Yeah, that makes sense. It's just a general guideline, basically.
Yeah, just a general guideline, yeah.
Okay. All right. Thank you.
Yep. Good. All right. So another common solution that we know very well, especially around here, is ocean water. Ocean water is primarily sodium chloride and H2O, although ocean water contains other components as well, but these are the majority components. Sodium chloride is the solute and water is the solvent. The solute in aqueous solutions doesn't always have to be a solid like sodium chloride. It can be a gas. So for example, carbonated water is a solution, and the solute in this case is carbon dioxide, all right? And the carbon dioxide is dissolved in the water. It's held in there under pressure. We'll talk about the solubility dependence, the dependence of solubility on pressure in just a few minutes. But when you release the pressure, the carbon dioxide can come out of solution, and that's the bubbling you see. So solutions, like I said, they have a very, very broad definition. Any homogeneous mixture of two components is considered technically a solution. So for example, you can have a gas and a gas where the solvent is a gas and the solute is a gas. Air might be an example of that, right? Mostly nitrogen and oxygen, all right? So a solution of two gases. You can have a solution where the solute is a gas and the solvent is a liquid, like we just saw, club soda, which is carbon dioxide and water. You can have solutions which are liquid within another liquid, like vodka, for example, is mostly ethanol and water. All right, ethanol is the solvent and water is the solute, right? You can have a solution in which the solute is a solid and the solvent's a liquid, like seawater we just talked about. And you can even have solid-solid solutions, but we won't really talk about those very much. Like I said, we're going to really focus in this chapter on aqueous solutions. Now, the first thing I want to talk about is why solutions form in the first place. Okay, it's kind of different than other things we've talked about, because if you remember last semester, I said that a lot of systems go towards lower potential energy, right? Right. If I have a pen and I raise it off and I drop it, right, the pen goes down towards lower potential energy, right? So we're kind of used to that in physics. You kind of learn that idea that systems go towards lower potential energy. Some solutions, when they form, the process is endothermic, okay, which means they absorb energy, which means that when the solution forms, it actually goes to higher potential energy, right? So here we have kind of our first example that we've seen of chemical systems that spontaneously go towards higher potential energy. So that's kind of like, this pen moving up, right? And going towards higher potential energy. So why do they form? Why do solutions form? Well, the real reason that anything happens is really not because they go to lower potential energy, even though we learned that in physics and we use that as a guideline even in this class. The real reason things form, the real reason that things happen is because of the dispersal of energy, all right? Everything that happens disperses energy. Anything that happens spontaneously disperses energy. And we're familiar with this, right? Like think about a hot cup of coffee in your hand. If you have a hot cup of coffee in your hand and you just let it sit there for a while, what happens? Which direction does energy go? Does it go from the coffee, where the thermal energy is concentrated, to the surroundings, or does the energy go from the surroundings and into the coffee?
Coffee to the surroundings.
Coffee to the surroundings, right? That's a spontaneous direction of energy flow. So all processes that happen because they disperse energy. And we'll talk a lot more about this later on in our chapter on thermodynamics. And it's pretty interesting, right? That's the direction. Nature just doesn't really like concentrated energy. So whenever energy is concentrated in one place, it tends to disperse. So it turns out that the reason solutions form is because of the dispersal of energy, all right? And here you have a simple system, neon and argon, two inert gases, right? They don't interact, right? There's no intermolecular, the intermolecular forces between them are very, very weak, right? They're only dispersion forces. And at room temperature, right, these things are moving so fast that the intermolecular forces really have very, very little effect, all right? But if you take out this barrier, they mix, right? They'll spontaneously mix. I'm going to call this nature's tendency to mix. So nature just doesn't like pure things, right? It likes things mixed up and kind of messy. And nature's tendency to mix is related to something called entropy, right? Which at its heart is energy dispersal. So you might say, well, why does the mixing here disperse energy? Well, each of these atoms has kinetic energy, right? They're moving around, bouncing around, they have kinetic energy. Notice that here, the energy of the argon atoms is limited to this side of this container, right? And the energy of the neon atoms is limited to this side of this container, right? But when we take away the divider, they're going to spread out. Why? Because that allows the kinetic energy of the argon atoms to spread out over the whole box, and the kinetic energy of the neon atoms to spread out over the whole box. So energy is more dispersed here than it is here, all right? And that means that entropy increases from here to here. So even though there's no change in energy, in other words, even though this is not energetically uphill or downhill, this process happens, right? It happens, why? Because there is dispersal of energy, and dispersal energy is the real king of determining what happens and what doesn't happen. So you can see that similarly if you have a solution of salt, let's say on one side of a container, and pure water on the other with a barrier in between them. You lift the barrier, you take it out, and these will mix to form a uniform concentration, okay? So there's this tendency to mix that always happens, all right? So we'll keep that in mind. Now, that is balanced with energetic considerations as well, all right? So we do have to take into account whether or not the system increases in potential energy or decreases in potential energy. And to do that, we have to go back to the intermolecular forces we learned about in the last chapter, all right? But now we're going to apply those same intermolecular forces to two different substances, right? So in the last chapter, we learned about dispersion forces and dipole-dipole and hydrogen bonding, but they're always within one substance, like within water or within ethanol and so on, right? Now we got to think, okay, these forces can not only happen, let's say, between two water molecules, but they can happen between water and some other molecule, right? Like for example, here we have hydrogen bonding between water and ethanol because they both contain hydrogen directly bonded to oxygen. So they can hydrogen bond with each other, even though they're different substances, right? Here are two hydrocarbons, heptane and pentane, and they have dispersion forces with one another, right? These two substances, even though they're different, they're both polar, so they can have dipole-dipole forces with one another. And then at the end of last time, we also learned about these ion dipole forces, which can occur between a ionic solute like sodium chloride and water, all right? So here's what we got to think about when a solution is going to form, right? We got to think about, let's see, okay, wait, quick question here, Alex.
So if something has hydrogen bonding, then does it also have dipole-dipole forces?
Correct.
Okay.
Yep, always. Yeah, this continuum, if something has hydrogen bonding, it has dipole-dipole and it has dispersion, right? Because everything has dispersion. So these are kind of inclusive as you go across. All right. So here are the kinds of things we have to think about. So in addition to this tendency to mix, which is prevalent in everything, right? We have to think about these interactions, solvent-solvent interactions, solute-solute interactions, and then when you mix these two substances, this new interaction, right? I sometimes use the analogy that, you know, these are your relationships in high school. You know, these are the relationships between college and these are relationships between high school. And then when you get to college, you have new relationships, right? And sometimes the strengths of those relationships will overcome the strengths of your high school relationships, right? And you'll do the Thanksgiving drop of your high school boyfriend or girlfriend, and you'll find someone new at college, right? So this is kind of the same thing. When you mix these two together, there's new interactions that can happen, right? And those new interactions are called the solvent-solute interactions. And we basically have to kind of compare the magnitude of these. So you can imagine if this interaction is super strong and this interaction is super strong, in other words, if the high school relationships are really, really strong, and then the new college relationship is kind of weak, right? Then there won't be a solution formed, right? Because these relationships dominate, or the strengths of these interactions dominate, and this one's weaker, so it won't form. If these are weak and this is strong, then a solution will definitely form, right? So we basically have several possibilities, right? If the solute to solvent interactions are stronger than the solute to solute and solvent to solvent interactions, in other words, if the new relationships are stronger than the old ones, then a solution forms, okay? And when that solution forms, the process is going to be exothermic, right? It's going to give off energy. If the new relationships are kind of the same as the old ones, well, it turns out a solution still forms. Why? Nature's tendency to mix. So even if there's no energetic advantage in terms of going towards lower potential energy, this is still going to happen. Why? Because of entropy, right? Entropy will drive the process. Now, if these are weak, right? If the solute to solvent interactions are weak and these are strong, then a solution may or may not form depending on the disparity here. If the disparity is small, you still get a solution forming, okay? And in that case, the solution formation is endothermic, and it's driven by what?
Entropy.
Entropy, right? It's driven by entropy, okay? But if this is a lot smaller than this, then the solution won't form at all, okay? So one kind of rule of thumb that we can kind of use to predict whether a solution will form when we mix two substances is the rule of thumb like dissolves like, all right? And here we're mostly talking about the divide between the nonpolar substances on the one hand and polar / hydrogen bonding substances on the other, all right? And what that means is that if you have a nonpolar substance and you want to dissolve it in a solvent, you should find a nonpolar solvent. If you have a polar substance and you want to dissolve it in a solvent, you should find a polar solvent, all right? And this is important. Like, for example, if you mix oil and water, right, they don't mix. Why is that? Water is polar, oil is very nonpolar, okay? So here's a bunch of solvents, different solvents we might use in the lab other than water. So water, of course, is polar and it has hydrogen bonding. Methyl alcohol, ethyl alcohol are polar and have hydrogen bonding. Acetone is polar. But then if you go to things like that are pure hydrocarbons like toluene or hexane, notice these don't contain any oxygen. Diethyl ether as well. If you draw out the structure of this, you'll find that it's pretty much nonpolar, all right? Carbon tetrachloride, similarly nonpolar. All of these solvents are good for dissolving nonpolar substances, right? So you know, for example, if you have grease on your hands, right? When you wash it with water, that doesn't do much, right? Because the water doesn't dissolve the grease. The grease is nonpolar. But if you put acetone or hexane on it, it'll dissolve the grease, okay? So this applies to vitamins. Yeah, hydrogen. This says hydrogen bond. This applies to vitamins. So vitamins like vitamin C, look at the structure here. Lots of hydroxyl groups, right? This big CO group here. You can tell from this structure that vitamin C is polar, all right? That means it's water soluble. That means you can eat as much vitamin C as you want, right? Some people take huge vitamin C supplements. It's never a problem, right? Because the vitamin C just dissolves in the liquids in your body. It's eliminated in the urine. It can make for kind of expensive urine because vitamin C is not cheap, but it's not going to hurt you, right? On the other hand, here's a structure of vitamin K3. Here you don't see any of the OH groups. You see mostly carbon and hydrogen. You see a couple of CO groups that are polar, but look, they're pointed against each other, right? So they tend to cancel. So this is very nonpolar. So this vitamin doesn't easily get eliminated in the urine, rather it builds up in your fats. And if you take too much vitamin K, you can actually get an overbuild up of vitamin K, and that could actually be harmful to your health. So there's some vitamins like this that are water soluble that it doesn't matter how much you take, but the fat soluble ones, you got to be careful and not take too much. Okay, so based on that, let me just throw a quick question at you and see if you're paying attention to me. I know you are because I can see you. Go ahead and try to answer this question. So remember, you're looking for the idea that like dissolves like, right? So which of the polar will dissolve polar, nonpolar will dissolve nonpolar? Okay, let's, I'm gonna keep this open, but let's look at A. You have lithium iodide and mercury, right? This is ionic. And this actually is a metal, right? So are those very alike? No, not very alike, right? B, you got C6H14. That's a hydrocarbon. What do you know about hydrocarbons? Are they polar or nonpolar?
Non-polar.
Nonpolar. Okay. And then you have Br2. Well, that's just two bromine atoms bonded together, right? The Lewis structure looks like that. What can you tell me about that? Is that polar or nonpolar?
Non-polar.
Nonpolar. Well, okay, there we go. There are two like things, right? So like dissolves like. These two are likely to form a homogeneous mixture. Let's just look at the rest of them for a minute. CH3OH. What do you see right there?
Hydrogen bond.
Hydrogen bonding, right? Very polar, very hydrogen bonding. C6, so this is polar H bond, right? What about C6H6? Hydrocarbon.
Nonpolar.
Nonpolar, right? So are those going to form a homogeneous mixture?
No.
No. And then lastly, D, carbon tetrachloride. Well, here you got to remember the carbon tetrachloride has a structure like this. Okay, if you draw the Lewis structure and you got the lone pairs on all these chlorines, right? But this carbon is tetrahedral, right? So even though this bond is polar, it's tetrahedral and the bonds cancel each other out, right? The polar bonds cancel each other. So this is non-polar, right? And what about H2O?
Hydrogen bonding.
Right, polar hydrogen bonding, right? So are those going to mix?
No.
Right. So the right answer is B. Okay, B. Does that make sense? Let's see, Laurel, did you have a question?
Yeah, it was about the vitamins.
Yeah.
Like, so certain vitamins, I guess you should probably take them in like an oil-based medium if you want to absorb it instead of a water-based. Would that be true?
The vitamins typically come in some sort of a tablet, and sometimes they can be oil-based, but that doesn't really matter as much. You can have them in different forms. The main thing is what happens after it gets into your body and your stomach, right? So your stomach is water-based, right? But
okay.
Still, the vitamins that you take that are non-polar can get into your bloodstream. They're carried there sometimes by proteins that can allow the non-polar substance to dissolve into the blood, right? But then they're quickly deposited into your fatty cells, right? In the fats, and then they can stay there, and that's what acts kind of as a reserve. So the danger of taking too much of a non-polar vitamin is you can build up too much of it in your fatty cells because it's not so easily eliminated in the urine the way a water-soluble vitamin is. Does that make sense?
Yeah, thank you.
Yeah, you're welcome. Okay, so eventually most of you got that, so that's awesome. Very good. Let's see, Helen?
Hi, I was wondering, why is the lithium iodide and the mercury, why do they not mix?
Right, so this is kind of a tricky one because mercury is a funny liquid because it's a metal, okay? And so the kind of interactions between the atoms are metal-metal interactions, which we really haven't talked very much about, but they're very different than ionic substances, right? So an ionic substance like this would dissolve very well in something like water that's very polar, right? But because this is an atom, it doesn't really have much polarity. Does that make sense?
Yeah, thank you.
Yeah. All right, very good. So we already kind of covered this in the last section, but just to summarize, if the solute to solvent interactions are greater than these, you get a solution and it's exothermic, right? Because it's energetically downhill. If these are about equal, you get a solution for them, but it's neither exothermic nor endothermic. If these are less If the solute to solvent interactions are less than solute-solute, then a solution may or may not form. If it does form, it's endothermic. It's energetically uphill. Okay. All right. What are some factors affecting solubility? So we already know, you saw the video hopefully before class, and it shows you that solubility is an equilibrium process, right? So when you put sodium chloride in water, right, it begins to dissolve, and it'll keep dissolving until the rate of dissolution equals the rate of recrystallization. And then that's when you reach equilibrium. And we haven't talked too much about equilibrium. We talked a little bit about it when we talked about vapor pressure. We'll be talking a lot more about equilibrium later on in this class. But remember from vapor pressure that at equilibrium, you have two opposing processes happening at the same rate, right? Two opposing processes occurring at the same rate, right? And so what happens when you get that is that you get a solution that has a constant concentration, right? So this will keep dissolving until that happens. That kind of solution is called a saturated solution. In other words, it's holding the equilibrium amount of solute. Okay. Let me just jump ahead here. You could have an unsaturated solution, of course, which means that it's holding less than the equilibrium amount of solute, right? So at some point, if you're making a solution, let's say you're making a sodium chloride solution, you add sodium chloride, it continues to dissolve, right? Eventually you hit the saturation point. That means that if you add more sodium chloride, it will no longer dissolve. It'll sit there as a solid, all right? Up until that point, you have an unsaturated solution because it continues to allow more sodium chloride to dissolve. You can also have a supersaturated solution. And these are not stable. Well, they could be stable temporarily, right? But common solution you can make that's supersaturated is sodium acetate. And what happens is that this is actually holding more than the equilibrium amount of solute. And you can actually get the solute to come out of solution by dropping in a little crystal of sodium acetate. So you have the solution, you drop in a little crystal of sodium acetate, all of a sudden it all comes out of solution, right? It all crystallizes out because it is holding more than the equilibrium amount, okay?
I have a question.
Yeah.
How is it possible that it can like hold more in it?
Yeah, have you a similar, and something that's kind of similar to this is, have you ever put like a water bottle in the freezer and had it not freeze? And then you take it out of the freezer and all of a sudden it freezes. It's kind of it kind of finds this this how can I describe it? It kind of finds this. It's almost like the analogy would be this: if you had a big hill, right, and you had a beach ball on top of the hill, and there was a little pebble here that prevented the beach ball from coming down, right? Then the beach ball would sit there, even though it's kind of this very unstable state, and just a little tap, right, and the beach ball goes rolling down. That's kind of the analogy, all right, for these kinds of solutions, okay? They really want to come out of solution, but what happens is that there's no place for the initial crystal to start to form. Typically, you need to form these in a very clean environment with no dust and no particles, and you can get a solution like this to form because that initial crystal requires what's called a nucleation site, a place for the little crystal to just begin to form. And if it's not there, it won't form very much. So, or it won't form at all. But then you put a little crystal in there and all of a sudden that becomes a nucleation site and boom, it all starts to form. Okay. Taylor.
When you said the supersaturated liquid and then it precipitates out all at once, is that all of the solute?
Yes.
Or is it just the overhead? Like
yes, it's all of the solute. And the solvent stays in. But this, I wish we were in class and I could actually show you a demonstration of this because it's pretty cool. These kinds of solutions can become so oversaturated that you can literally take this and pour it out and it'll immediately form a crystal, and the crystal will trap the water so that it won't spill. It'll actually form a solid mass. It's really cool. I should try to find at least a video to show you. You might want to just look this up sometime. Supersaturated sodium acetate solution, and watch the video. It's pretty cool. Okay.
All right, will do. Thank you.
Yeah. All right. Let's see. Now I want to switch gears a little bit to factors that affect solubility. Okay, so we're going to look at two factors. One is the temperature dependence of solubility. All right, and the temperature dependence of solubility affects solids dissolving in water and also gases dissolving in water. Okay, and we're also going to look at the pressure dependence of solubility. But the pressure dependence, in other words, different pressures affect only gases. Okay, so we'll look at the temperature dependence for both solids and gases, and then we'll look at the pressure dependence for gases. And I see a question from Tyler. Tyler Smith?
Yes, hi.
Hi.
Earlier on, when you talked about the solutes and like determining if they're endothermic or exothermic.
Yeah.
I just wanted to know, what was that diagram?
This one?
Okay. Yeah.
Yeah. So what I was just showing here, and so this slide was kind of pretty similar to this slide that we went over, right? It was just comparing the interactions between the solute and solvent, sort of in my analogy, the new interactions when you go away to college, compared to the solute, solvent interactions, which are the old high school interactions, in my analogy, right? And so if these are stronger than these, then you always get a solution that's exothermic. If the interactions are all kind of the same, you still get a solution that's really neither endothermic nor endothermic. If these are a lot weaker than these, then you may or may not get a solution, but if you do, it's going to be endothermic. So that's what that was.
Okay, all right.
Okay.
Thank you.
You're welcome. All right, so let's look first at the temperature dependence of solubility. All right, so for solids in water, which is really what we're talking about in aqueous solution, although it occurs for other things too. So solutions, solids in liquids, let's just say. Solubility increases with increasing temperature, right? And you kind of know this, right? If you want to dissolve sugar in water, is it better to have really cold water or hot water?
Hot water.
Hot water, right? We'll dissolve it better, okay? So here are some curves of solubility, which means this is the number of grams of solute that you can dissolve in 100 grams of water of different solutes, all right? And so you can see this as a function of temperature, right? So for example, at room temperature, sodium chloride, room temperature is about 25 degrees. So you can dissolve what? Maybe 35 grams of sodium chloride in 100 grams of water, right? If you add more than 30, that's a saturated solution, right? If you add more than 35 grams, it won't dissolve because you'll be beyond the saturation point, right? Unless you can have the conditions such that you can make a super saturated solution. But again, that's not very common, okay? And you can see that they're different ionic compounds will have different solubilities, but almost all of them, for almost all of them, look what happens as temperature increases, right? The solubility increases. You can dissolve more and more and more, okay? Now, there are some exceptions, all right? Like Ce2SO43 right here. Its solubility actually decreases with a decreasing temperature, but those are rare, all right? I just put one here so you can see that they exist, but generally speaking, the solubility of a solid increases with increasing temperature. Sophia, question.
On the pre-lab, there was one of the, I can't remember what compound, but the curve went like to a peak and then it went down. Is that because of the temperature, or is it because it reached a point where it was super saturated?
You know what? I'd have to go back and look at that exactly. I'm not sure, Sophia.
I can describe it. It was like it went from, for example, 0 to 50, and then it would go down, like it would start going down. It would reach that peak and it would start going down again.
Okay. Yeah, that's possible. It's a little complicated to explain why. There's actually two factors that determine solubility, the dependence of solubility with temperature. One of them is actually the change in entropy, okay, that happens when the substance goes into solution. So we already know that a lot of dissolving is driven by entropy, right? So typically when a solute like calcium chloride, let's say, for example, dissolves, entropy increases, like we said earlier, right? But a substance like this, and perhaps a substance that's on your lab as well, when they go into solution, they actually produce more order. They produce less entropy. And that's why the solubility goes this way for those substances, all right? We'll discuss this a lot more when we start looking at changes in free energy later on. Right now, it's a little hard to explain because we don't have the mechanisms by which the tools to explain it. But when we do, I'll come back to that. And if you remind me, and I'll try to explain it more fully. Is that okay? Seth.
Thank you.
Yeah, I was just wondering, when solubility versus like gas and a solid, do they have like an inverse relationship to each other?
Let's talk about that. We're going to get that in just a second. We'll get to that in just a second. Okay. The main thing here is that for a solid and a liquid, solubility increases with increasing temperature, right? If you guys take organic chemistry next year, you'll often use a technique called recrystallization to purify some of the compounds you make in lab. So organic chemists often synthesize compounds, right? Like, for example, you can synthesize aspirin, or you can synthesize whatever compound you're going to synthesize. And when you synthesize a compound, you get your products, and they're often not totally pure. So you want to purify them. So one way to purify them is to dissolve them at a high temperature where they're soluble, and then you let it cool. And as it cools, you get what's called recrystallization, right? The solubility falls down, it gets less, and the solid comes out of solution. And when it comes out of solution, it forms these really nice crystals, and these crystals tend to reject impurities, right? Because the crystal structure is such that in order to make the crystal, you got to have the same substance over and over again to make the crystal structure, all right? So that's one way to purify substances, recrystallization. All right, now, what about gases in a liquid? How does that solubility depend on temperature? Well, it turns out the solubility of a gas in a liquid decreases with increasing temperature, right? So this is why your warm Diet Coke will go flat faster than your cold Diet Coke, right? And you saw that in the video, right? You saw them both being poured, and you saw that the warm one bubbled out more. Why? Because the solubility of carbon dioxide is less at the higher temperature than at the lower temperature. At the lower temperature, more of it stays dissolved, all right? You can see here solubility of two gases, carbon dioxide and acetylene here. As temperature goes up, solubility goes down, right? This is why summer fishing at Lake Kachuma can be pretty slow sometimes, right? I don't know if any of you ever go fishing at Lake Kachuma here in our little backcountry, but that lake can get pretty warm in the summer. What happens? The solubility of oxygen goes down, right? And if the solubility of oxygen goes down in the warm temperature, that means the fish are not as active, right? Because the fish need oxygen from the water, right, to be active, right? That's part of their metabolism. So if that solubility of oxygen goes down, when it gets too warm, right, the fish are not going to bite as much, right? No, so in the summer, if you go fishing in Lake Kachuma, you got to find the really deep spots where the water is cooler and you can get more oxygen in the water, and therefore the fish are more lively in those spots, right? Now it is a balance. In the winter, on the other hand, fishing can also be pretty slow because the water gets so cold, and fish regulate their temperature based on the water temperature, right? They're not warm-blooded like mammals, right? So their body temperature is the same as the water temperature, and the water gets too cold, they also kind of get slow and lethargic because the chemical reactions occur too slowly. So the best times for fishing in Lake Kachuma are the fall and the spring, where it's kind of in between, right? Where you have enough oxygen in the water because it's still cold enough, but it's not so cold that the fish get lethargic. Okay, these are just some more gases at different temperatures. All right, I see a question from Sophia. Was it Sophia?
Yeah, I mean, so in solids and liquids, I can see it because it mixes faster. The solid and the liquid, everything's moving faster. But then in gases, why does it happen that solubility goes down?
Yeah, because again, it's a thermodynamic question, and it's related to the change in free energy, which is related to the change in entropy. And so when a gas leaves a solution, it actually increases entropy. So when it goes in a solution, it actually decreases entropy. And that process becomes more spontaneous. Well, if delta, so here's the equation. Delta G is equal to delta H minus T delta S. We'll get to this a little bit later, but you may have seen it if you've had another chemistry class. When this is negative, that's spontaneous. So this gives you the temperature dependence. If delta S is positive, then as temperature gets bigger, this gets more negative. So if the entropy increases for the process, then the temperature dependence is going to be such that as temperature increases, it gets more spontaneous. But if delta S is negative, like for a gas going in the water, then you get the opposite effect. As temperature increases, it becomes less spontaneous. Okay, but again, we'll get to that again in more detail later. Sorry, I can't completely really answer your question very well. Okay, good. Here's a question for you. Go ahead and try to answer this. All right, looking good. Try to put in your answer in the next 10 seconds or so. I'm going to end the poll. Okay, I'm going to end it there. share results. So you can see that most of you got the right answer, which was A. All right, some oxygen gas bubbles, but a few of you predicted that both would happen. The main thing to answer this question is to understand that the temperature dependence of the solubility of gases and solids is different, right? The solubility of a gas decreases with increasing temperature. The solubility of a solid increases with increasing temperature, right? So if you dissolve both a solid and a gas at room temperature and you warm it up, what happens to the solubility of a solid as you warm it up? It becomes more soluble, right? So that means it just stays dissolved in the solution, right? On the other hand, the solubility of a gas becomes less soluble as you increase the temperature, right? So what's likely to happen is that the oxygen gas bubbles out of solution. In fact, this is exactly what you see. Have you ever paid attention to what happens when you put water on a stove and heat it up? Eventually it'll start to boil and you get big bubbles coming right out and you get the boiling. But long before it reaches 100 degrees, you'll see small bubbles starting to come out of solution, right? And if you measure the temperature, it won't be 100 degrees. Now you might think that that's kind of like pre-boiling, but it's actually not. Do you know what those small bubbles are? Anybody?
Are they just air from the pressure, like natural pressure?
Yeah, they are nitrogen and oxygen that's dissolved in the water because there's nitrogen and oxygen in air. So there's nitrogen and oxygen dissolved in water. And as you heat it up, that nitrogen and oxygen begins to come out of solution, right? And those are those small bubbles, right? Some people have sometimes, let's say they go to the pet shop and they get a new goldfish and they say, oh gosh, I should boil the water for my fish before I put them in there, right? So they boil some water and they let it cool down. They put the fish in and the fish dies, right? Why does the fish die? When you boil the water, you've taken all the oxygen out of it, right? If you boil the water, you got to let it sit around for a few days or maybe a day or two so that the oxygen will come back in and then it'll be okay, right? Because again, the solubility of gases decreases with increasing temperature. Okay. I'm glad that I'm glad most of you have not heard of that. But it does happen sometimes. All right. Let's see. All right. So then the other factor that affects solubility is pressure. Okay. And this only applies to gases in liquids. Okay. So, and we'll just say it this way: for a gas, the solubility of a gas increases with increasing pressure. Okay. Solubility of a gas increases with increasing pressure. So if you have a solution of, let's say, CO2 in water, and you have some CO2 in a cylinder like this, and you increase the pressure, what happens? You start to push more of the CO2 molecules in a solution. The rate of dissolving increases compared to the rate at which CO2 is coming out of solution. And that'll happen until the concentration gets large enough here and the pressure gets low enough that equilibrium is reestablished. But at that point, there'll be more carbon dioxide in the solution, right? So the solubility of a gas increases with increasing pressure. And there's an equation that describes that. It's called Henry's law. Henry's law, the solubility of a gas is equal to a constant times the partial pressure of the gas. All right. So, let's see, these constants are here. Table 14.4 lists the different Henry's constants for different gases. So this is the solubility, and the units of solubility are moles per liter or molar, right? This is a constant. The constant has units of molar per atmosphere, right? And of course, this is the pressure, and the pressure has units of atmospheres, right? So this tells you that as the pressure of the gas increases, the solubility increases in direct proportion, right? So if you double the pressure, you can double the concentration of gas that's dissolved in the liquid. Okay, a couple of things related to this. When you open a can of soda, right? The soda contains dissolved carbon dioxide in the liquid, right? It's held there by the pressure. The minute you open the soda, you release the pressure. So when you release the pressure goes down and the solubility goes down. Because the solubility goes down, that means that the carbon dioxide bubbles out of solution and you get your carbonated beverage, right? This is kind of a very tragic situation that happened related to this. This is a lake in Cameroon, Africa, and it's called, the name of the lake is Lake Nyos, and it's a volcanic lake, which means that it's basically the mouth of a volcano that filled with water, all right? So the volcano is still sort of active, at least to some degree, enough that it produces a lot of CO2, right? So the carbon dioxide is constantly bubbling into this lake out of the mouth of the volcano. So that this water in this lake is very highly carbonated, all right? But at the bottom of the lake, you have all the pressure from the water above it, right? Because it's a very, very deep lake as well. So what happens to the solubility of the carbon dioxide at the bottom of the lake? Because of the high pressure, the solubility is very high, right? So at the bottom of the lake, you have very, very highly carbonated water. Now, for some reason in 1986, something happened, maybe a small eruption, maybe a landslide, they really don't know what, but something happened that caused the layers of the lake to mix a little bit. So imagine what happens. You get a layer at the bottom that's saturated under high pressure with carbon dioxide, and now it moves up. Now the pressure on it is less, right? So if the pressure is less, the solubility of the gas is less. So carbon dioxide comes out of solution. Well, of course, when carbon dioxide bubbles, it causes more mixing, right? So the whole lake began to churn and release large amounts of carbon dioxide. Now, carbon dioxide is heavier than air. And if you've ever seen a dry ice machine, you've seen how carbon dioxide basically sinks down and moves along the bottom. So unfortunately, the carbon dioxide that was released from here sank down and went into the nearby valley where it basically suffocated the population there. Hundreds of people died and lots of cattle and things like that because of this tragedy. So what happened is that scientists went in and put in a vent, and this basically circulates the water all the time and doesn't allow those very, very high carbon dioxide concentrations to build up at the bottom of the lake. And now that doesn't happen anymore. But that was a real tragic event that happened in 1986, directly related to this idea. Okay, let's do an example using Henry's law. All right, so here we're given that a gas has a Henry's law constant that's equal to 0.112 molar per atmosphere. And it's asking us, so this is given, it's asking us to find the volume of solution that's required to dissolve 1.65 liters of the gas at a pressure of 725 torr, right? And a temperature of 25 degrees Celsius, all right? So we want to find the volume, right? Now, we know from Henry's law that the solubility of the gas is equal to KH times the partial pressure of the gas, right? So it's giving us the pressure, right, which is this. It gives us Henry's law constant, right? So we can find the solubility of the gas, and that'll give us how many moles dissolved per liter, right? And it's asking us to find what? The number of liters. So the only thing we have to figure out then is, well, how many moles how many moles need to be dissolved? So can we get moles from this? What does that remind you of from last semester?
PV equals nRT.
Correct. V, P, and T, right? And you know, whenever you see those three things together, you go, oh, okay, that's PV is equal to nRT. So in this case, you want to find N, the number of moles. That's PV over RT, right? So the first thing you can do is find the number of moles. So N is equal to PV over RT. So that's equal. This you got to convert to atmospheres. So when you do that conversion, and I'm sure you all know how to do that, so I won't carry it out for you. That's equal to 0.954 atmospheres. The temperature has to be in what?
Kelvin.
Kelvin.
Kelvin, right? So you just plug into here and you get 0.954 atmospheres, right? Times 1.65 liters. Oh, my pen is running out of ink. 1.65 liters. Divided by R, 0.08206 liter atmosphere mole Kelvin, right? Times the temperature in Kelvin. All right, so you carry that all out. Notice atmospheres cancel, liters, Kelvin. You end up with moles, right? And you find out that this is equal to 0.0644 moles, right? So you want to know, okay, what volume will it take to dissolve this many moles? Well, you can use this guy to figure out the solubility, right? The solubility of the gas is going to be equal to the Henry's law constant, which is given, right? 0.112 molar per atmosphere, right? Times the pressure, 0.954 atmospheres, right? So that cancels, and that gives you 0.1068 molar, all right? So in other words, under this pressure, the solubility of the gas is that, right? And you know that that means 0.1068 moles per liter, right? Remember from last semester, molar is moles per liter, okay? Hunter, I see you there. I'm gonna introduce you in just a second, okay? So 0.106 moles per liter is the solubility. So now you know the number of moles, and you know the moles per liter, so you can get liters, right? So you go 0.0644 moles, right? Times 0.1068 moles per liter, and your moles cancel, and you get 0.603 liters, right? So it takes 0.603 liters to dissolve that total amount of gas. Does that make sense? All right, let me go ahead and actually I have a question for you to do, but before I do this, did I do that wrong? 0.603, yeah, 0.603 liters, that's correct. Before we do the question, I want to introduce our third TA. If you remember, last time, the second day of class, yeah, I guess that was a week ago today. You met a couple of our great TAs. You met Shea and Thomas, and Hunter wasn't able to be with us that day, but he's here right now. So I just want to give him 1 second because he just got out of another class, and I think he can't stay very long. So I just want you guys to get a chance to meet him and let him introduce himself. Hunter, you want to introduce yourself real quick?
Yeah. Hey, everyone. I'm Hunter. I was a TA last semester, too. I've already seen a lot of your faces. I'm really looking forward to working with you all this semester. Yeah, and my tutoring hours are listed on the Canvas page there, but also outside of those, feel free to send me messages and stuff like that. I'm pretty responsive with all that. But yeah, I hope to see you all there. It's going to be a good semester.
Yeah, Hunter took my class last year and aced every single exam and finished at in the very, very top of the class. And so he's really bright, and he's just a great guy. So he's good at explaining things too, which really helps. So if you need help, there's lots of places to go for help. I'd rather have you go to one of the TAs or to my office hours than to just start Googling stuff, right? Because we're gonna lead you in the right direction and to help you to learn how to solve problems and learn chemistry. When you Google something, who knows what you end up getting. Okay, thanks, Hunter. Thanks for coming by.
Yep, thanks. See ya.
I'm going to go ahead and start this poll here and let you go ahead and work on that. So go ahead and try this.
What are the options?
The options aren't there. And unfortunately, this gives the answer. Shoot. All right, well, never mind. Well, go ahead and try this and just confirm. The answer is D, but just go ahead and give it a try and make sure you get that answer. Okay, and then I'll show you how to do it. My bad. Sorry about that. I'm going to end this polling. Just go ahead and try it yourself. The main thing here, of course, is to get you to try some of these things. And I forgot to put the answers in this slide, obviously. Okay, well, the main idea is to use this equation, right? And basically, you're being given the pressure of the gas and the solubility, and you're asked to find K, all right? So all you got to do is you say KH is equal to the solubility of the gas, right, divided by the given pressure, right? So you just plug those numbers in. The solubility, it says, is 0.12 molar. And the pressure is 3.5 atmospheres, right? So the value you get for K is 3.4 times 10 to the minus 2 molar per atmosphere. All right. Hopefully you're all able to get that. Any questions? Does that make sense?
May you move your pen a little bit? Yeah, thank you.
Okay. So solutions, what's going on here? Okay, our last topic for today, and I'm not really going to go into it too much. I'm just going to introduce it real quick because you're going to watch a video on this one before the next lecture. So I'll just introduce this topic and then we'll call it a day. As you know, solutions can be concentrated or they can be dilute, right? And so we need a way to specify solution concentration. And so far, we've been using molarity, right? Moles per liter. But that's not the only solution concentration unit that we can use. And we often use different units beyond that as well. Molarity is the one you already know, and it's just the number of moles of solute per volume of solution, okay? But in addition to that unit, we'll be using molality. Molarity is big M, molality is small m. Molality is moles, but instead of per liter of solution, it's per kilogram of solvent. Now, this unit is particularly useful because it doesn't change with changes in temperature. So molarity can change when temperature changes, but molality doesn't. Because if you think about molarity, right, if I have some solution, right, and it has some volume, right, some volume, and you have some number of moles in here, right? What happens when temperature rises, for example? Well, the density of substances tends to change with temperature. Typically, density goes down, which means that the volume actually goes up. So if the volume of the solution goes up, but the number of moles stay the same, what happens to the molarity?
It gets smaller.
It gets smaller, right? So the molarity can change with temperature. But molality doesn't change because it's per kilogram of solvent, all right? And so that doesn't change with temperature, and that's another unit we'll be using. Mole fraction also doesn't change with temperature, and mole fraction is the amount of solute divided by the total amount of solute and solvent, both in moles, all right? Mole percent is just the mole fraction times 100%. And then we have 3 common units here that are all really closely related, and they're all parts by mass, all right? And they're mass of the solute divided by the mass of the solution times some multiplication factor. So for example, if I have 10 grams of solute in 100 grams of solution, right? Then my parts by mass, when we talk about percent, we say percent by mass, right? Would be equal to 10 grams divided by 100 grams times 100%, right? And that's equal to 10%. Well, that makes sense, right? If I have 10 grams of solute and 100 grams of solution, that's a 10% solution, all right, in parts by mass. In mass percent. Now, some solutions are much more dilute than that, and in which case we need units that account for that. So these have different multiplication factors. Parts per million, the multiplication factor, instead of being 100%, is 1,000,000. Parts per billion by mass per billion is the multiplication factor is 10 to the 9 or 1 billion. Okay, so very, very dilute solutions we'll describe using these units. Okay, all right, that's just a quick introduction to units. Don't worry if you didn't follow all that. I've thrown a lot at you already this hour. You'll see a video on this, and then we'll get into it in more detail, including some examples next time. Okay. Very, very good. Are there any last minute questions before we sign off? Ryland.
Yeah, so in that example problem that you went over with the PV equals nRT, my 155 is a little rusty. Where is the R coming from?
The R is this constant right here, and it's the ideal gas law constant.
Okay.
And it's just that's the value. So whenever you see R, that's the value, 0.08206 liter atmospheres mole Kelvin. So it's just a constant of proportionality, and it has that value. And we'll be using it a lot, so it's a good one to know.
Thank you.
Yep. Okay, everyone, I want to thank you. Thank you for being here. Thank you for your awesome attention. And very weird, right? Because we're only meeting today and we don't meet again until next Monday. So it's a short week, but nonetheless, you have lots to do. Keep track of my to-do list that I'll be sending you the end of every week for the following week, and stay up with that stuff. And thank you very much for coming, and have a great day and a great weekend. Bye.